30 minutes.
Thank you, Gondel. So this is Abdelhak from Concordia University. So today I will be presenting. So actually this work has been done by my student Jashan, and he couldn't attend because of the visa issue anyway. So, okay, let me just, okay, why it's not working? Yeah. So the main aim of this presentation basically is how to adjust the server-side QUIC parameters based on some metrics that we are getting from the client for better quality of experience. And as you might know that we have multiple problems with TCP. Actually, this is not my update, because yesterday I updated my slides. I'm not sure. It will be good if you can open the updated slides. Sorry. Yeah, I sent them yesterday. Okay. Exactly. Yeah, those are the ones. Okay, so we have actually many problems in TCP, and this actually two of the major problems, which is like high latency because of three-way handshaking, which takes 1 RTT and a half, plus the TLS negotiations, which takes around 1 RTT, and the head-off blocking, which, you know, if you have a packet loss, obviously the sender needs to retransmit that packet, and that blocks actually the other like objects in the pipe, and that might degrade the quality of experience because it might lead to rebuffering, right? Actually, QUIC is proposed to solve this issue, and it's built on top of UDP, and it requires only 1 RTT to open a connection with also TLS negotiations. It has amazing features for video streamings applications, for example, multiplexed streams where you can send these streams in parallel. You have actually connection migration where you can migrate from Wi-Fi to LTE and from LTE to Wi-Fi without any session reset, right? So therefore, I would say like QUIC open new opportunities to improve the HTTP adaptive streaming applications. If you look to the literature, we have two, I would say, major optimization that people work on. The first one is to improve the quality of experience, of course, is client-side optimization where we improve the player, for example, ABR, bandwidth measurements, buffer management, playback speed modules, and we have server-side optimization where we design a new congestion control, right? However, the optimization is kind of decoupled, right? Where one is the application layer optimization, the other one is transport layer optimization. And do you think that's enough this optimization? Actually, the response is no. And do you think that deploying QUIC will give you a good quality of experience? The response is no. You need to do a lot of kind of tuning, a lot of engineering work, a lot of research and development, actually, because the client-side optimization and the server-side optimization might conflict with each other. And especially for streaming 4K and 8K, I would say, content, and during the high volatility, I would say, condition where if you switch from 4G to 5G and again from 5G to 4G, that actually distracts the quality of experience a lot. As well as using kind of a fixed server-side parameters also might not work for all the network conditions. So this is actually some of the QUIC challenges that we have seen for adaptive video streaming. It's lack of the application awareness, to be frank with you, and that impact actually the ABR decisions, for example. There is no cross-layer sharing between the application layer and the transport layer to optimize video streaming applications. We rely actually on static configuration that hinder quality of experience at the server side, especially for 4K and 8K streaming videos. We might have network instability. That's because of the burst transmission of QUIC server. Usually that actually sometimes overwhelm the queues of the router, and that lead to the congestion which impact actually the application layer. We have also problems with bandwidth measurements. Sometimes if the QUIC sends this data actually with some pacing, right, because we have also pacing rate, which is a part of the congestion control, it might impact actually the bandwidth measurement when we have actually measurement regarding that things. So what we have proposed here is CAQ, connection-aware QUIC, where we actually kind of coupled what we are doing at the application layer as well as with transport layer. How? Basically, we are sending some informations from the clients using CMCD custom header. We encrypted it, and we sent all this information from the client. As you can see, it's around 6 like max chunk size, playback speed, max mean buffer level, maximum resolution, and segment duration. So we put them in a custom CMCD header, we encrypt that, and we send it to the server. So once the server gets that the HTTP request, it decrypts first and extracts those information and do the adjustment of the parameters, which I will explain. So this, as you can see, how the pipeline for CAQ works. So we have actually the client, QUIC client, we have the QUIC server. In the client, we get the playback statistics, every segment download, I would say. And then we incorporate some of these statistics that I have shown already in the HTTP request, and we encrypted it using CMCD stuffs. And then we transmit it. So we will have the modified HTTP request, as you can see here. So once that modified HTTP request reaches the server extracts the information after of course, the decryption, and then adjust some parameters, as well as adjust the pacing. And I will explain why we did that and the algorithm that we run at the server side for this adjustment. So this table shows like the parameter that we are sending from the player and the adjusted parameter by QUIC server. So this is how the algorithm works. So first of all, the server needs to decrypt and extract the playback status, right? And then we initialize the QUIC transport parameter. As you can see, this initiate max data and max stream data is 2 parameters to max chunk size, and then we check if the resolution is 1080p and the chunk size is more than 1 MB, which means we are streaming 4K, I would say, the videos. Then we increase the maximum datagram size to 1460 to avoid some fragmentation. So also we do the check if the segment duration is more than 6 seconds. So we extend the idle timeout to 10x the segment duration, because we find that the QUIC usually for the large segments cut down the connection, and that actually impact the quality of experience. And then that's also one of the good optimization that we are doing, where we compute or we match the pacing rate as per the stream speed of the client. That's one thing. And the second thing, we check if the buffer is less than 10% of the maximum buffer, we double the pacing rate, such that the server will push the data as fast as they can. So, and to kind of refill the buffer and avoid the rebuffering. And then we continuously run this in a loop. So this actually why we did that, why we put this initial max data and max stream data equal to the max chunk size that we extract from the MPD anyway. So this actually ensures that the client can process the data efficiently without being overwhelmed. This kind of flow control, right? If you know flow control in TCP. And we found that lower values can increase the latency as well as rebuffering, right? Because you will have like kind of more data and more acknowledgement, right? And that might lead also to the underutilizations of bandwidth. So why we put also the max datagram size to this value, 1460, which the common one in TCP when we stream 4K or 8K videos. So basically we, to prevent this, what we call fragmentation, as well as to enhance the data transmission, because we are reducing the number of packets, right? And this buffer-driven pacing is to avoid rebuffering, mainly when we have actually less than 10% of data in the buffer at the client side. And this idle time what actually save us a lot, because as I said, in the larger segments, we've seen like usually the QUIC server kill the connection, and that actually impact the quality of experience. And we don't want this to happen. So this is the extended version that's actually kind of under submission. It's also one of, it's a big paper anyway. So where we are trying to ensure a good cooperation between the APR at the application layer, the AQM from the network layer at the routers, as well as the congestion control transport layer at the server side. And we use actually deep reinforcement learning to do these adjustments. For the experiments, this is the setups. We have actually 3 Dockers. The first Docker runs 5 Go Dash player. The second Docker is mainly to shape the bandwidth between the client and the server. And with Docker 3 is the QUIC server. And we have 2 types of TC network traces, which we get them from real-world network traces. We have the 5G, 4G high volatility trace, and that's actually the average and the STD. And then we change the value every 1 second. And for the server side, we deploy 2 traces. One is Twitch, and the second one is Belgium, and those are the values. For the video content, we use these 4 video contents because later you will see each client, as you can see there, the client setup. For example, client 1 run this or stream NR video, client 2 stream NR video, client 3 stream STC video, and we tested for both scenarios, VOD and low latency, and that's the playback speed that we have set for these scenarios, just to mimic real-world scenarios, right? For the ABR, we use actually pensive, throughput-based, and BBA, buffer-based. For the QUIC server, we use QUIC, which is standard QUIC, and QUIC star with CAQ enabled. For the congestion control, we use QUIC and Reno, which is supported by QUIC anyway. The experiment duration is 100 seconds, since these are the evaluation metrics, and these are actually the ABR ladder. Here we go for the results. So this is the server-side results, and this average over 3 runs. As you can see, our solution, which means QUIC star, there, achieves actually better throughputs and reduce the RTT. Thanks to that, I would say, dynamic adjustments of the QUIC parameters, right? And this shows the client-side solutions. The 3 graphs, as you can see, the congestion control is QUIC, the ABR is pensive, DRL-based, and the server-side trace is the LTE Belgium. So here the main, I would say, results, as you can see, the QUIC start increases the VMAF by 9% and the bitrate by 15% while reducing rebuffering. So these 2 graphs here are like we just changed, it's the same scenario, low latency, but we just changed the ABR. We still achieve like the same, I would say, kind of trend of results where QUIC start with CAQ enabled, improve the VMAF and the bitrate while achieving actually 0 rebuffering. And this actually the same, but for VOD scenario. In VOD, since we have actually enough buffer, so we don't have any rebuffering for both scenarios, either QUIC or QUIC start. But as you can see, we are still see the same trend of improvement in terms of VMAF as well as the bit rates. Okay, so this is just a final note. So we designed CAQ to ensure a QUIC server parameter adjustment for better quality of experience. So it's a kind of cross layer where we share the application layer metrics with the transport layer metrics, I would say, thanks to the CM-CD custom header. And the adjusting pacing rate helps a lot to avoid, I would say, or reduce rebufferings. I think that's all, and thank you.
Thank you, very interesting. I'm wondering, you're adjusting these parameters on the fly. Are all the QUIC stacks are actually capable of doing this? Because I would assume that there are certain parameters, if you like switch them down, like what is the stack supposed to do, like drop packets from the buffer or things like that?
Yes, so as I shown in the slides, so some of the metrics, the initial one are fixed. Sorry. Yeah, let me use this one. Yeah, some of the parameters are fixed. For example, the max chunk size is fixed, right? We know so therefore this will just change once, right? But some parameters, let's say pacing rates, those are dynamic. Yeah.
Okay, just 2 clarification questions. So you mentioned at what point that improve RTT, and that really confused me. RTT is not a fixed thing between the server and the client?
So it's a kind, we reduce the RTT compared to the standard IO QUIC when we enable CAQ. Because when you you double or you adjust the pacing rate, the server will send the QUIC stream as fast as it can, right? Because you are doubling it. And you know what's the pacing rate is just what's we called managing the gaps between the datagrams, right? So yeah, so that helps reducing the RTT a bit.
The idle time.
Idle time, yes,
okay,
exactly,
okay. No,
exactly, exactly. That's the right wording. Sorry for that. Yes, yeah.
Okay. And then you mentioned that you are adjusting the datagram size, but it's not clear to me if you are using QUIC streams or QUIC datagrams in that experiment.
Actually, we are using QUIC streams.
QUIC streams. So you are adjusting the MTU.
Yes, exactly, exactly,
okay,
exactly.
Thank you.
Yeah, welcome.
Serving as relay. Any other question?
Thanks. So have you thought through the fact that under mock we use QUIC and we want to do ABR, we haven't done it yet, but it seems much of the benefits you're getting here might actually apply to mock and might actually be better because we have a return channel that's not limited to the segment requests, but it could be a much faster update. So if the client could hint to the relay, the content characteristics as you're doing here, do you think we could get the same or even better improved benefits under a mock scenario?
Yeah, I believe so because all of our work is on, I would say, transport layer. And actually we're experimenting with all the QUIC implementations. Queen, IO QUIC, and VFST, all of them. I think we investigate 10 with a different congestion control, either heuristic-based or learning-based, like ORCA or the Meta one, which is DRL-based. So I would say, yes, it will improve, and I believe we will achieve similar results. And I have my students is working on mock now. Okay.
Hi. Yeah, interesting talk. I was curious about the pacing. I understood on some QUIC implementations it was happening at the interface layer, so you wouldn't be able to do it per connection, that sort of pacing necessarily.
Okay, so for the pacing, if you look how we calculate that duration depends on the congestion control that you are deploying, right? So if you are, I think, deploying the QUIC, it will be like CWND times MSS by, I think, RTT. That's how they compute it in QUIC. And for the BBR, I believe it's bottleneck bandwidth. That's what I recall. I hope that I'm correct, but that's what I recall. So here, adjusting the pacing rate for us, it will be, yes, it's peer connection, and the main idea there is like to protect clients that has like lower buffers, right, such that we can send data as fast as we can. However, it has also some issues, which is it can also overwhelm the buffers of the routers, and it might lead to congestions, right? But at least in our experience, we haven't seen that. But there is a case where that happened actually for us. So, but this is just the initial design. Now we are, I would say, refining our design, where we also incorporate the AQM at the router.
Okay, I was just saying that the pacing, is it always implemented by the QUIC stack itself, like with, or is it implemented at the interface level? Because it's just, if it's interface level, then you
actually
can't.
It's a part of the congestion control.
Because with, say, for example, BBR, the way that's implemented is in the interface typically.
Okay, because the implementation has been done by my students, the thing that what I'm 100% sure that the calculation of pacing rate is different from congestion control to another congestion control.
Yeah.
And then I give you like the equations for both QUIC and BBR, right? So yeah.
Okay, and the other thing was the...
No, maybe you can continue later.
Yeah, sure.
Because we are
running over time.
Extremely late. So it's no break and soon no lunch. Okay. And then sorry, but this is not my fault.
So yeah, we can discuss offline. Yes. We will provide also the implementation open source. So once the papers are like, we have, like, this paper has been accepted, so we will provide the code source open source as well. So, yeah. Okay, I think my second presentation is about bandwidth measurement in mock. Okay. Okay, let's go. So I believe already we'll discuss the mock architecture where you have like publishers and you have subscribers, which are kind of clients, and you have the relays where they cache the data. So the main purpose of mock, as I understand it, is like to unify the protocol stacks for different use cases, let's say video conferencing, live streaming, gaming, as well as video on demand. But now, like, the more focus is on low latency and ultra low latency streaming. It uses like publisher subscriber workflow, and it organizes the media per objects, group, and track. Here we go. So you know, measuring an accurate bandwidth is not easy task, actually. That's what we have seen in media over QUIC. And an accurate throughput measurement is very critical, especially for the ABR. If you have a wrong throughput measurement, that might lead to a wrong ABR decision, and that might lead to a negative quality of experience, right? And it's also actually very necessary for throughput smoothing and prediction, which I will make the distinctions between this, where we have the measurement first, then you have to smooth, and then you have the prediction, right? So how does it work? So first of all, we have the subscriber, which measure the bandwidth, as you can see, the red one, right? The throughput measurement, and that's actually the focus of this presentation, on that link between the relay and the subscriber, not between the publisher and the relay. That does impact, that's the end-to-end throughput, but our is the last kind of what we call last mile throughput measurements. We have also the relay, which advertises the available track, which is constrained by the publisher relay bandwidth, and the publisher is the one that encodes the track, right? And here we have two modes of transmissions. We have a push-based for the new, I would say, subscribe for the new object, and we have fetch, which already we'll discuss it, for actually the old objects, right? So the main interest of this presentation on that link, right? How to measure the bandwidth accurately. So there are many factors that impacts the subscriber throughput measurements. I actually divided them in three main factors. We have network factors, we have QUIC factors, as well as application factors. For the network factor, we have actually latency and jitter, right? So both of them might actually hinder the throughput measurements. Packet loss for sure, because if you consider retransmitted packets during the measurement, that also will break the measurements. For the congestion control, it might also actually impact the measurement, because the congestion control needs to adjust, right? The CWND, the congestion window. If you have multiplexed streams, also we found that it hinder actually the throughput measurements at the client. If you have a lot of retransmission in case of lossy environments, as well as packet reordering, right? So you need to implement a logic that detects that, and mock has it already, right? And for the application layer, we have chunked media, and that's because of the CMAF, where we will have some gaps, and if the player considers those gaps in the download time for that track, it will actually lead to an accurate bandwidth measurement, and we explore that problem actually in two papers, ACT and LOL Plus for Dash. And if you have an ABR that switch a lot between actually the qualities, it also might impact the accuracy of the throughput measurements. Here we go. So we have the measurement where we use this formula, size by download time, right? And then once we have, let's say, 10 sample or 20 sample, we pass that to a smoother, right? Which is, let's say, exponential moving average, or exponential weighted moving average, or sliding window moving average. And then we use machine learning and deep learning techniques to predict, which means ahead. 1 second, 2 seconds, 3 seconds. Obviously, if you have wrong measurement, that leads to a wrong smoothing, and that leads to wrong predictions. Okay? So here the main idea is like to have accurate measurements that lead to accurate smoothing, and that lead to accurate predictions. So if you look to the literature, we have, I would say, 4 types of throughput measurement techniques. We have the application layer, or the application level based here, where we calculate the throughput by measuring the time taken to download the entire media segments by the download time, right? And then the second thing, which is the packet level based, where it works on like QUIC packets itself over a sliding window. We have congestion level based, where actually we calculate the throughput by leveraging some metrics from the sender side, like CWND, the congestion window, and RTTs and other stuffs. And we need, this metric has to be observable by the subscriber. And we have the hybrid, which kind of mix these two, okay? Okay, so this actually table shows the K metrics used for each measurement type, the formula that we have used, and the limitations, okay? So here, actually, for the application level, one of the limitations, like, as I explained, if you have a lot of off periods between the tracks, right, that lead to a wrong, I would say, download time, and that will impact the measurement for sure, because in the formula, we have to divide the size by the download time, right? For the packet level, as I said, it will be within a time window. You extract the sizes from the payloads, and you try to do this formula. But that will be distracted by if you have a lot of burstiness in your traffic, a lot of retransmissions, and also you have sensitivity against the window that you decide to use. For the congestion level, similarly, you need an accurate RTTs, as well as you need this information to be sent to the clients, I would say, by the server. You need to enable that, right? And for the hybrid, if you have an accuracy either in this one or in this one, the measurement will be wrong. Okay, so what we propose here, we propose hybrid flow. A hybrid flow is, this is the formula that we have used. I will not go in the detail, but feel free to ask me. So this is general formula that we are using, which is kind of novel hybrid throughput measurement algorithm that couple the packet level and the CC level. So we get this matrix from actually the relay. And this is the formula where we have a weight for the packet level measurements, and we have a weight for the congestion level measurements, and we have the TH Kalman, which is the throughput, the smoothed packet level throughput via Kalman filter, and we have the THCC adjusted, which is the adjusted congestion control level throughput incorporating loss rates and RTT variations. We want to kind of penalize like the throughput CC if we have like a lot of loss and a lot of RTT variations, and these are the two weights. So yeah, this is how we compute the throughput CC adjusted, where we have the throughput CC times 1 minus loss rates. So that loss rate, EMA, basically we smoothed the loss rate using the exponential moving average times 1 minus the standard deviation or the deviation in the RTTs. And this how we calculate the weights for the congestion level throughput based. I will not go into detail, but feel free to ask me later on. And actually, the weight that we assigned for the packet is 1 minus WCC. And this, you know, a famous formula for exponential moving average, right? Okay, so how does it work? So we have the relays pushing the data to us. So the first step we do like what we call active probing, but that depending on the condition, right? Because we are like using a certain number of packets. If we have a less number of packets, obviously that might lead to an accurate throughput measurement. Therefore, we need to kind of doing active probing at the subscriber side, right? But if we have enough packets to consider, then we are good. The second thing that we filter out the retransmitted packets, thanks to kind of the sequence numbers, right? As well as we apply kind of penalty if the packets are out of order, and then we apply the exponential moving average to smooth the loss rate that we use later on to adjust the throughput measured by the congestion control. The step 3, we will measure this in parallel, the throughput packet level and the throughput congestion level. And for the throughput packet level, we give it to a Kalman filter to smooth it, and then we will get the TH Kalman. And the throughput congestion control, we adjust it as per, as I said, the smoothed loss as well as the STD RTT, and we get throughput congestion And then we make the formula that I have shown before. And in step 4, we will have the throughput measured by the hybrid flow. This is just why we did all these steps. Okay, and these are the inputs that we need for the hybrid flow. So we extracted the packet level through actually a wrapper around QUIC API, and for the congestion control, we send them through CMSD to actually from the relay to the subscriber. And for the network condition parameter, which is loss rate and RTT, we also extracted them through a wrapper around QUIC API. For the experiments, so we use the Sepehr implementation from Ali Group. So thank you guys for providing that, because it has the ABR, it has like some throughput measurement. So thank you guys. It was like very beneficial for us, and we reduced a lot of time, to be frank with you. And actually these are actually the different kind of setup that we used here. And I will not go here more in the detail, but let me jump. This is actually the ladder that we have used. Just actually for the mock objects is 1 frame, and for the CMOS segment is 2 seconds, which is like kind of mock group, right? And as I said, we use the mock RS modified, and this is the link implemented by Sepehr. This is the results. As you can see, the lower is better. This result showed actually the measurement error where we take the actual, because we have the actual throughput from the trace itself, right? Minus what's actually measured by the algorithm, right? As you can see, for the 3G, for the 4G, as well as the satellite, this is actually from, I think, Victoria University, which is real-world satellite traces. Hybrid flow achieves the lowest measurement error in these 3 scenarios compared to the application level, packet level, and CC level. So these are the improvements, okay? And then, as you can see, we deployed the we tested the hybrid flow when we switch the congestion control. And to be frank with you, BBR give us the better results compared to QUIC and Reno in bandwidth measurement. Of course, all of them follow the trends in the 3G trace and similar to in other traces. However, here the error is less for BBR. Okay, and that's because of how each, I would say, congestion control adapts to the network condition and how each congestion control computes the CWND. And then, now let's move to the prediction. As I said, if you have an accurate measurement, that will lead to an accurate prediction. And here we use for smoothing SWMA, and we take the 10 recent samples for the prediction, and we implemented all of these techniques. Some of them are statistical model like XGBoost. Some of them are like machine learning models, and some of them are like deep learning models, right? This one, patch TST, which is transformer-based model. So the best results here is from patch TST and XGBoost. Similarly, for the satellite traces, we can't see the same trend. However, the patch TST requires GPU, and XGBoost runs over CPU. So the final notes is like hybrid flow so far is good, but it has an issue, which is the hyperparameters. Okay, to be frank with you, we are still working on that, where we are using machine learning techniques to fine-tune those hyperparameters that we are using. And do we need a complex bandwidth predictor? No. XGBoost achieves actually great results for time series predictions, right? And it runs on CPUs and very fast compared to the patch TST, which is transformer-based that requires GPU. And what's next? Actually, this is kind of, I would say, done. We have a paper is under submission now, where we did a large-scale experiments covering, I think, 6 or 7 QUIC implementations with different congestion controls, with different ABRs, with different network conditions. And also, we are aiming to extend the hybrid flow to consider multi-flow and multi-path QUIC. Thank you.
Appreciate your presentation and the level of complexity, and it sounds like you might actually be willing to take on something that I'm terrified to do, but in
Sorry
Quinn,
for that, you know.
No, it's great. No, the RTT stuff is great, but I'm staring at Quinn and I'm looking at bytes in flight, and I'm just wondering if you're also intrigued by looking at bytes in flight per connection as a way to model this as well. I mean, is that something that you might actually engage with as well? The Quinn bytes in flight data?
Yes. So for
too complicated.
Yeah, that's true. So to be frank with you, to extract those values, it takes a lot of time for us actually, and my students actually spend, I think, more than 4 months working on this just to design that wrapper. Initially, we used QLog. It was amazing. However, the problem of QLog that we found, like the real-time reporting of those metrics, right? So the QLog reports these results, what we found, like at the end of the session. But now I think it can also work in real time. So he spends, but also thanks for the mock iris community that they provide actually a wrapper for Queen APIs. Actually, it's there. Actually, we based on that as well, and we extended it. First of all, actually, we tried with dash over QUIC. That's the first thing before we moved to mock. Actually, right? So yeah. Yeah, there will be more details in the paper. It's under submission, so yeah.
Hi, interesting. I just had a question with connection sharing. Say, have you considered that as part of your design? I mean, I guess it can be fairly easily integrated.
No, for this is just one client.
Right, okay. Yeah. But I mean, the client, yeah, I mean, I guess you have one client, but potentially if it's in a web or you've got multiple sharing.
Okay, I will let you know. We have another congestion control that we designed separately that takes care of the fair share.
Right.
Just to let you know, that's also is under submission.
Okay, good. Sounds good.
Like yeah, we have a couple of papers that are under submission, but I will announce them through my LinkedIn once they're accepted. So.
Okay, thanks.
Yeah.
Okay, thank you. Let's.
Okay, thank you so much.
Next one.